I was taught the same thing, but there's actually a formula for that downhill. Do you know it?
No,
None of us are taught that. Because when I saw the formula, I was like, nah, that's not right.
But the circumference is too big, so you won't actually notice the difference.
But there's a formula. Don't you want to know the formula?
I should know the formula, but I don't.
No, but I
know that there is a formula.
Yeah, I can offer it to you. Because it's right here on our flyer, actually. It's they use trigonometry. And they say that over the 10 miles, there should be 60 feet of curvature. You know, you've seen 10 miles over a lake, and it's flat on the other side. You can see the...
But sometimes when you're walking, you won't...
Sometimes? I'm just doing science. I'm not wanting to theorize. I'm not wanting to theorize.
You're good.
Yeah. I don't want to theorize too much, because theology is for religious people. You know, I'm trying to break people from religious belief in things that you can't prove for yourself. And you have to take government's word for it. NASA is government. You have to take their word for it, that they've been to the moon, and we can show definitely that they've never been to the moon. So many things wrong with the moon landings. They've never been back in 50 years when the technology in your phone is thousands of times smarter than the technology they used back then. So if we could fly out then with that old craft, why can't we fly out now? Why can't Elon Musk go out there with people?
But have you seen the NASA people jumping from space?
You mean the Felix Baumgartner? The Felix Baumgartner jump, the Red Bull jump?
Yeah.
So there's a guy called Neil deGrasse Tyson. He's quite a popular scientist on TV, and he says that guy was never high enough to see the curvature of Earth. According to him, what you're seeing is the fisheye lens from the outside. But when he jumps out of his cupola, if you go back and watch the footage, you'll realize there's just 2 seconds of footage from the camera that's inside his cupola, which is not a fisheye. And you see just a flat line across outside from 150,000 feet or whatever he was. So no, we can't see curvature. We amateurs have taken balloons up to 120,000 feet, and everything still looks flat. The first person who ever went to 10 miles high was a guy called Picard. They used his name in Star Trek, by the way. A guy called Picard, a Frenchman. He went up 10 miles, and the first words he said when he came back was, "It looks like flat with upturned edges." That's all I could see from 10 miles up. Now I've flown a lot. Recently I flew from South Africa. It's 11 hours, 1/4 of the distance away around the globe. So whatever amount of curvature you think you can't see now, over 1/4 of the distance is like going from 12 o'clock to 3 o'clock on your clock, right? And that's a 90-degree change in my aspect. So my water bottle should have started, say, that way and ended up that way.
Yeah.
If I was really doing what they say, we're doing this. But if my plane goes like this and I put a spirit level on the floor, I zero it on the ground, and then watch it for 11 hours, and it says it's nose up 1.5 degrees for 11 hours, where am I ever going down?
Okay, but how do you explain sunrise and sunset?
Okay, sunrise is like this. So let's just say we're standing on the beach in the water right now, and I'm standing here, and you guys are standing 10 meters in front of me, also further into the sea. Okay, is the wave going to hit you first or me first?
That's first.
It's going to hit you first. So as the wave starts to come, it's like the morning rising of the wave. Think about how the wave is going to initially the low part of the wave, then the wave is going to crest over your head, and then it's going to set behind you. And as it's setting behind you, it's starting to arrive at me now. Just because you got smacked 10 meters back there, I haven't been affected by the wave yet. So we think that the sun is like an energy. I think it's an energy wave, a pulse that comes across the land, east to west, or it goes round. I don't know, but it's easy to say that it's a small light. That if I was in a stadium with a torch, for example, you'd only be able to see my torch. You know, from a small, it would only illuminate a section of and then as I moved around the stadium, I would be illuminating different sections. So like that is how it might look.
Have you seen the test that they did with the light and the camera and the hole and the wooden box?
Yeah.
To test
you mean the double split, or
there was like 2 pieces of wood, like a couple miles apart, with the light shining through one, and then the camera through the other one.
Okay,
so that's if it's a curvature, this curvature. Basically, the light's supposed to go through. If the Earth is flat, the light's supposed to go through, and the camera should catch the light through the hole because they're both on the same height. They couldn't see it at first, so they lifted up the light, or lifted up the camera, sorry, and then they were able to see as there was curvature. They proved that there was curvature. It was actually flat earthers who did the test, and then they were proven wrong with that test.
So we've done a few laser tests, quite a lot of laser tests over 20, 30 miles. People have also taken photographs of cityscapes in the sunset from 50 miles. Then in France there's a mountain, Carigou, that can be seen twice a year because the sun sets behind it, and you can take a photo over water, 150 miles, something like that. So the railgun that the American military they use a laser to point from one ship to another ship. It travels at Mach 15, and it can get up to 100-mile range. And so those ships have to be seeing each other because the laser is reaching out 100 miles and touching the ship in the distance, and the sabot or the round will hit that spot where it is. It's not curving, it's not dropping, it's just one poof, and out it goes, and in seconds it's there. So we say that's great evidence. So what happens with lasers typically is they scatter. So you can see, like the National Geographic one, where they debunked the curvature, or they said there's curvature because we're seeing it. It's actually, we're not seeing it spray like this, and it means it must be bending or whatever over what. No, I don't. For me, those things aren't conclusive. And that experiment, I mean, I'd like to look at it, but I'd probably be able to pick it apart. So so I'll bring it back to the maths. Is that if you think it's there, then you should be able to measure it. It can't be possibly there. It has to be there. And what we're offered by NASA is a almost perfect sphere. And an almost perfect sphere, like a football, is bending at the same amount all of the time. There's never a flat spot on a football. No matter how big you make that ball, it's got to maintain its curvature. Yeah, and that curvature is going to be equal all the way around it. So we should be able to measure it, and that measurement should start from, if you were standing on a beach, it's to start from the first meter, first mile, the first 10 miles. You should be able to immediately say, because it's bending the same amount everywhere on the globe, it's bending by this amount. So a ship that travels 5 miles away from you, you're going to say he's dropped by 10 feet, 20 feet, or whatever it is. You can look at the formula yourself, but you're going to say he's dropped by 10 feet, 20 feet. And eventually at 5 miles, 6 miles, you won't even be able to see the ship anymore. And they say, that's it, it's 50 feet now. We've lost all of the ship. Okay, but then we can bring a powerful telescope into play, or a camera with a big zoom lens on it, and bring that ship right back into focus, the whole of the ship. Yeah. So we're saying now, is this not just obscuration by atmosphere, and that as things go away in the distance, they become smaller, they shrink down, and because you're standing at the very bottom of a portrait picture, which has got miles high up into the clouds and miles into the distance, you've got a very low angle of resolution onto the images in front of you, which is why they use the crow's nest, the tallest point, to find land first. Why? The higher you go, the further you see. You see? But the shorter you are, the less far you can see. So what's the shortest part of the ship? The bottom. So that's why you use the shorty at the bottom first, and the guy with the tallest head at the crow's nest, you see him last, because it's just slowly going away in your angular resolution. But get in a hot air balloon, go up 50 meters, and you see the whole ship again, because your angle of resolution on that has changed. We could do the similar experiment on a flat section of this square, say, where you put your head on the floor, your camera on the floor, and you realize that if someone gets 100 meters away, you're losing their feet, and then you're losing their knees, and then you're losing their hips, and then you're losing their head. And that's how angular resolution works, as well as things, shrink in the distance. So no, pretty much everything. So it's 8 inches per mile squared is the formula, guys, for curvature. I don't agree with it, but that's what they offer us as being, that's how much should be there. 8 inches in the first mile, which means if you've got a dinghy and you're going from here to the other side of the lake 1 mile away, your boat's actually going to go down 8 inches according to the stupid maths. But the clever thing is that when you turn around and go back, you're going to say, okay, I went down the first journey A, I went down 8 inches. Now I'm at point B, and I turn around and go back to A, I'm going to go down 8 inches again. Yeah. Bullshit. You can't do down both ways.
I really respect your examples. I really respect what you say.
Cool, man.
Yeah, you're very good at arguments, debates.
I talk about electromagnetic theory more interestingly. I think that we are electromagnets inside an apple. We are little apples inside a big apple. And I'll give you a flyer. You can take it away if you want to on our website. Sure. You can check it out.
Nice one.
Cool, man. Take one for your friends.
Thank you so much, bro. Cool. Have a nice one. Thank you so much.
Nice talking to you. Go well, man. Know that you are the center of creation. There should be no master here but you. You are the master. Hi.
Hiya.
How are you?
I'm good.
Have we met before?
Yeah, in Birmingham.
Oh.
On Friday, yeah. She was there.
Gosh, yeah.
We had a little chat up.
Sorry.
Yeah, we had that conversation with the vicar. Do you remember?
That's right. I want to put that on. I haven't had a chance to put that out yet. I need to put a load on here.
We should put the papers and the rock.
Yeah, let's.
I recorded that as well, sir.
Sorry?
I recorded that.
You did.